All right, welcome back to statistics. So today we are going to talk about, with this video, we're going to talk about confidence intervals. Okay, so it's going to be a little bit hard to swallow at first, but I guarantee you it becomes a little easier as you go through the problems and as you get a little bit more familiar with it. Okay, so let me go ahead and share my screen. And we can talk about what that's going to mean. All right, let's see, how do I want to do this? We want to say something clever, like, okay, so the way I usually introduce this, if you take your car to a mechanic and they say, well, it's going to cost us $600, it's going to cost you $600 to fix your car. That's an estimate, and that's great, but you might be, the mechanic might be a little bit, they might hedge their bet, like, I haven't looked at it yet. I could say that maybe it's going to cost between $550 and $650. Okay, so you can say, I'm pretty sure it's going to be somewhere, it's going to run you somewhere between $550 and $650. Okay, so don't take these as any levels of confidence. Okay, pretty sure it's like, okay, whatever. So just realize I'm making up words to kind of try to fit my narrative here. Okay, we could get a little bit better. Maybe the mechanic says, well, right, I'm like, what's one level up from pretty sure? Okay, let's see, we could say something fairly certain. Okay, and that might tell you like a little bit more, right? So you might get off for $500, but it might cost you all the way to $700. But it's better than that $600 estimate, because if the bill comes back at $700, you're like, wait, you told me $600. I'm like, it's not that legally binding. Okay, you're stuck. So this is the bill. Okay, we could keep widening this. Okay, we could go from $400 to $800. Okay, almost certain. Okay, but now we're getting into the realm of like, okay, you gave me an estimate somewhere between $400 and $800, but this is getting less and less useful to me, because like, I might get out of here for $400, but you're going to tell me that I might be up here at 800. Let's do two more. Let's do the 200 to 1,000. Okay, it can cost you anywhere from $200 to $1,000. Like, that's not effective as an estimate. I mean, you're very, you could be more and more certain as a mechanic. If you're giving this estimate, you are more and more certain that this is going to be, that this is going to be, it's going to fall within here. Okay, so you say 99% sure it will be somewhere between 200 and 1,000. We could just go, we could keep making this window bigger and bigger and bigger, right? We could say, well, we can go from, well, it might cost you nothing to $1,200. Like, okay, so you as the mechanic, you're willing to bet your life on this, okay? But you as the customer, I'm like, that doesn't help. Okay, that's too big of a margin. But that's the kind of thing that you're looking at. We're looking at it from the mechanic's point of view. So if I'm going to tell you, well, it's going to be some number, okay, I'm 100% certain that it'll be some number between I might owe you money and you might owe me a lot of money. But well, I could say like that's 100%. Okay, like that is useless as far as information goes. So the more confidence you have, the wider margin that you're going to tell somebody. Okay, because we're not changing with a confidence interval. You're not changing what you know about anything. You're not getting a better estimate. All you're doing is saying, well, we're going to make the target big enough that I can't miss, or that my acceptable amount of missing, or I'm under an acceptable amount of missing. Okay, so that to go with that one. Generally, we have a 90% confidence interval, we have a 95% confidence interval, and we have a 99% confidence interval. There are some other ones that get used like 98, 80, okay? So these will sometimes get used, but for the most part, these are your big three, okay? So this one, I'm telling you, like, you know, I'm over here. Like, I'm going to be wrong one time in 10, okay? With 90% going to be correct, but my margin is actually going to be pretty narrow, okay? So you think about like throwing darts at a dartboard. Like, I might miss one out of, I'll miss all the time, but you might miss 1 out of 10 times with a dartboard like this. But if we make the dartboard and the bullseye just a little bit bigger, right, you might only miss 1 out of 20 times. And then if we make it really big, okay, with a really big bullseye in here, you're going to only miss 1 out of 100 times. Okay, so even on a throw that might not be so good, you're still going to be able to get it in the target. Okay, and that's really what we're doing, is like for as this gets bigger and bigger and bigger, we're making this bullseye larger and larger and larger. So technically, we don't really talk about 100% confidence interval, okay, but they'll be like, well, I'm sure the dart will hit somewhere on this planet. I can say that with 100% certainty. So the smaller the confidence interval you have, right, is the smaller the interval, right, the less certain you can be about covering your actual average. You're covering your actual mean. 95% is like one of the good balances between I'm only going to be wrong 1 in 20 times, and it's a small enough interval that actually is still somewhat useful to the person who is receiving this information. Okay, so what we're doing is we're trying to say, well, we have a mean in this class. We have an average, right, plus or minus some margin of error. Okay, every confidence interval looks like this. Okay, it might be a standard deviation, it might be some other parameter, it might be some other statistic rather, not a parameter, statistic. It might be something else. It may not be X bar. Okay, but it's whatever you're looking at, plus or minus some margin of error. Okay, so for chapter 8, for our purposes, what we want is we're going to say X bar plus or minus. I'm just going to write it down and we'll explain the symbols in just a moment. Okay, times sigma over the square root of n. Okay, so standard deviation, you've met this one before. Okay, standard deviation. Okay, specifically the first section in chapter 8 talks about when sigma is known. Okay, so sigma is a known parameter. Okay, and I can imagine it's begging the question, like, well, what do I do if sigma's unknown? That'll be in section 8.2. Okay, we have n, this is our sample size. So it's kind of like the last section where we're talking about groups and we're trying to cover a sample average. Okay, X bar is going to be our sample average. Sample size here, sample average. Okay, and then this Z alpha over 2 business. Okay, we're going to talk about that. So this is called a confidence coefficient. Okay, and you don't really need to know exactly how they calculated these. I mean, I will show you, but what's going on here? So if I say Z with 0.05 here, okay, or Z with 0.05 divided by 2. Okay, that would be Z 0.025. Right? What that means is that my confidence interval, okay, by the way, this number here, this is an indicator. We used to look these up on tables, and this would tell you what column. Okay, this would tell you what column you're going to look at. Do not multiply, divide, plus, minus, take a logarithm of. Do not do anything to this number is only to tell you which column to look at. But we use a calculator now, so we don't really need this anymore, except to tell you like what kind of confidence interval we have. Okay. So if I go out 2 standard deviations, right? Empirical rule, how much data is within 2 standard deviations? 95% within 2 standard deviations. How much is left over in this little spot here and this little spot here? That was 5%. So we got to break it in half because we got to get a little bit in here, we got to get a little bit in there. So there's 2.5% here, there's 2.5% there. That's where the 0.025 comes from, is this 2.5%. So what a 95% confidence interval is going to give us, okay, that's a 95% confidence interval. What that means is that our interval is going to cover the true mean 95% of the time, okay? So we're going to say that we expect the interval to include mu 95% of the time, all right? So we expect the interval to include mu 95% of the time. That's why we say the confidence coefficient, we're checking this out, because what we had to do was we had to do this problem. We'd have to do norm inverse 0.025 for standard normal. Remember, standard normal is when the average is 1, or 0 rather, and the standard deviation is 1, right? Mu is equal to 0, standard deviation is equal to 1. This is standard normal. And we could type that in, right? So this is where we're going to get the confidence. You're not, everything is going to be done with the calculator, but we need to know like what notation the book is using so that you're not going to get, it's not going to be too bad for us. So distributions, inverse norm, 0.025, mean of 0, standard deviation 1. Done. Okay, and the 3 decimal places, confidence coefficients are almost 3 decimal places, negative 1.96. Well, this is negative 1.96. What do you think this one's going to be? This is going to be positive 1.96. So for a 95% confidence interval, right, we're going to have x bar. This is going to have to be given, okay, plus or minus the z alpha over 2. Well, we're going to look that up on our table. We're not, but we're going to say this is 1.96 times sigma over the square root of n. That's the standard error. This guy, wasn't it? Okay, so that's what we're doing there. Okay, so we're going to be using, okay, to do something like this, we're actually going to be using our calculator to say stat. We're going to go over to test, and we're going to say z interval, okay? And it's going to guide us through it, okay? We can either put in data, we're going to need that later, okay? Or put in stats, okay? I chose stats for this one. So this would mean that my standard deviation is given, it's 1. You're going to get that out of the book. X bar is going to be whatever we have here. We're going to have a sample size. And at sea level, right, that's 0.95. That's the 95% confidence interval. And all you have to do is fill these values in, right, and then press calculate, and that's going to give us a confidence interval. So we have a 95%. So even though X bar, or sample average, was 3.27, I'm betting on 95% of the time, right, that our whatever the true average is going to be somewhere between 2.78 and 3.76. Okay, and that's how we're going to be interpreting this. So this is a little bit more of an interpretation, but students have generally been better off interpreting this than interpreting some of the earlier stuff in the class. Okay, I think we've all been given an estimate from a mechanic oh, it's $600, and they have them come back and give you the bill for $800. Like, if I'd only known, right? So they can't do that too much. I mean, there is some amount of responsibility for the mechanic to do that, but at the same time, they're not. They probably haven't taken. They may have taken freshman stats. They might know this. Okay, I don't know, but they're not going to be legally bound by it. But you also can't have a mechanic that constantly tells you 600 hours and then bumps up the price a couple $100 every time. Like, if that happens, like, maybe get better at estimating, or maybe something else is going on. Like, if it's always above, maybe that says something. But you can't do that. Okay. So that's the idea of what we're doing. Okay. And the first problem they give us is a terrible problem. So what we're going to do is we're going to jump right into the easier problem, I hope. Yeah, at least the first part of this is the easier problem. Okay, so and we'll backtrack into the other ones. Okay, but I just want to give you an idea of, like, what are we talking about? How are we doing a problem? What's the interpretation? So according to a recent report, a sample of 360 one-year baby boys in the United States had a mean weight of 25.5 pounds. Assume the population, so you're going to see this a lot in this section. Assume the population standard deviation is 5.1 pounds. Okay, and then we're going to do some stuff with it. Okay, so let's just write down what we have. Right, we have an n is equal to 360. Okay, we have a mean weight is equal to 25.5. Okay, we have a standard deviation of 5.1. Okay, and what do they want us to do? The first thing they want us to do is find a 99.5% confidence interval. Here's another casualty of the 20th century. Because you can calculate any confidence interval you want just by changing a selection on your calculator. They typically don't always use 95%. When we had to look this thing up on a table, it was easier to keep using like the same numbers. But it's still a pretty common technique. It's a pretty common choice to make 95% the standard. Okay, again, this is going to be a very wide confidence interval because we're very sure, right? 5 times out of 1,000 we can be off. Okay, and the only thing we have to modify, right? The only thing we can change, we can't even change this. We have this information. The only thing we can change is how big is the target going to be. Okay, so let's go ahead and type this in. So we're going to have the way I would put it in paper, right, is x bar plus or minus. I'm going to look this up in a little bit. Okay, times sigma over square root of n. So we would say, well, this is 25.5 plus or minus. Sigma is 5.1 over square root of 360. Okay, the calculator is going to do this for us. Okay, watch. So we're going to go to stat. We're going to go to tests. Okay, we're going to go down to where it says z interval. Okay, z interval. Okay, so we're not going to put data in. Okay, that would be, if we had a list of numbers, we would choose data. We don't have a list of numbers. We have some basic descriptive statistics here. So we're going to say that. What was our average? Or what was our standard deviation, rather? Our standard deviation said it was 5.1. Okay. What was our x bar? It was 25.5. Okay, we got that from the original problem. What n did we have? We had a 360. Okay, now my confidence interval, we have to convert this into a decimal. So 99.5 is going to be 0.995. Okay, we just move the decimal over twice. So we're going to have C level, confidence level, 0.995, and then we're going to go ahead and hit calculate. Okay, so what we're going to be doing here, right, is we have 24.745 to 26, because our sample size is huge, that's why. 26.255. Okay, so we are 99.5% certain that whatever the true mean, the true average, okay, the actual mu, okay, of the weights of 1-year-old baby boys in America is going to be somewhere between these two numbers. Okay, so the way your book is going to write it is going to be that 24.745 is less than mu is less than 26.255. Okay, we have a 99.5% chance that this number is between these two numbers. Okay, now this isn't changing. Okay, it's a parameter. This is constant. Okay, we took a sample here. Samples can change, right? We change the sample, we change the mean. So whatever this number is, we have a 5 in 1,000 chance of not getting it right. But it could be we took a bad sample, right? And maybe mu is sitting here, and we have our two numbers are over here. Okay, so that is a possibility. Okay, so the values we got here, let's look at what they want us to type in. Okay, they want 24.745, and we want 26.255. I believe that's what we got. All right, so we'll check. There you go. Okay. Should this confidence interval to be used to estimate the mean weight of all 1-year-old babies in the United States? Did we include the girls? No. So no, we really shouldn't do this, okay, because we kept our sample to just boys. So we shouldn't. We didn't include everybody. We didn't include both genders. We didn't include boys and girls here. Okay. This didn't say anything about race, so we're not going to worry about that because it said that they just picked a sample. So we're going to assume that they did it fairly, but they restricted it to 1-year-old baby boys. All 1-year-old babies? No, we didn't include any girls. So that shouldn't be. Okay. And then based on this confidence interval that we made, is it possible, or is it likely, not just is it possible, is it likely that the mean weight of all 1-year-old boys is greater than 28.3? Okay, so a lot of times people use the word statistically significant. And in this day and age, significance means that it's important. But that is not what that word meant when they came up with that lingo. Significant just means, is it noticeable? Okay, so if you told me 26.255, I think the average baby weight is 26. Like, I can't argue with you. That is within my interval. If you want to say, well, I think my interval is 25. 25 is still in my interval. I can't tell the difference between these two numbers as far as the scenario goes. Okay, both of these numbers are inside of my interval. They're not statistically significant. I can't notice a difference between these two. Okay, but 28.3, that is way outside of my interval. So I don't have any evidence to justify that this is going to be a higher number than the ones that I already have. Okay, so you can say, I think it's 26.1. Like, I can't argue. But I think it's 27. Could you please tell me your results? Okay, why do you think it's 27 and not 26? Because my data says it's 26. Now you may have a different sample. That's okay. But my evidence, my numbers, my calculations show that it's 24.745 to 26.255. If you want to come along and say 28.3, please bring some evidence, right? Show me your sample, show me your study. Okay, I can show you this one. So, well, I did that one. Okay, so show, but you have to show me. So as far as I'm concerned, 28.3 is a ridiculous number. We can't, no, it's not ridiculous, but I mean, we're not going to accept just their good word that's 28.3. We have to say, well, it's got to be somewhere between here. So you have to bring me some evidence to say, this is why I think it's higher. Okay. So we're going to say it is not likely the mean weight is greater than 28.3 pounds. It's outside of my interval. Okay. And that's how you read this thing. All right. So there we have it. All right. Let's try another one. Okay. So this is a similar problem. Okay. So in this case, we have a sample size, right, of 316. Okay. We're told that it's between the ages of 38 and 82. Okay. So in this case, we just have a sample of 316 patients. We don't know anything else. So we're just going to assume that it's a simple random sample, and that people of different races, people of different genders, everybody was capable of being a entry into the study here. Okay. So they were given a combination of drugs. I am not pronouncing this. Okay. And they achieved a mean total reduction of cholesterol of 0.92 millimoles per liter. Okay, so our average reduction, okay, is 0.90. Okay, we had a standard deviation, a population standard deviation of 0.18. Okay, now I'm not certain as to how much cholesterol that's actually reducing. I know that in the previous chapter, right, we were looking at about 200. So if this is your mean reduction is about 1 out of 200, that's an interesting drug you've got there. I don't know if that's worthwhile, but this probably doesn't mean that. So let's be fair to the story here. Okay, we're going to construct a 99% confidence interval for the mean reduction of total cholesterol. Okay, so we have a bunch of descriptive statistics. When we go to our stats, turn this thing on, go ahead and hit stat. We're going to get tests. We're going to go to Z interval. Okay, and we're going to change some numbers around here. Okay, so my standard deviation here, right? The standard deviation was 0.18. 0.18. Okay, you don't need the leading zero. They just trained me now. Okay, my average was 0.92. Okay, and right, my sample size was 316. Okay, what they wanted a 99%. Okay, great, make a liar out of me. I told you 95% was the standard. They haven't used it yet. Okay, so there we go. Actually, for medical stuff, it is closer to 99 is their standard, but academia, where we sit, it's 95. All right, our interval 0.893 to 2.94608. All right, this is my 99% confidence interval. All right. So we're going to type these numbers in. How many decimals? Oh, they wanted 2. Again, if they didn't tell us how many decimals is their mean, how many decimals is their standard deviation, I would guess 2. So we're going to say 0.89 to 0.95. Okay, so the mean reduction is somewhere in here. Okay, 89 to 95. Okay, so we want 0.89 to 0.95. Okay. Should this confidence interval be used to estimate the mean reduction in total cholesterol for patients over the age of 90? Well, they were 82. So no, you shouldn't. Okay. You should not be used to do that because 90-year-olds have a different physiology, right? Well, they may have a different, I don't know if they do. They may have a different physiology than 82-year-olds. Okay, the drugs may not work as well on them. So no, you shouldn't be used to do that. All right. Based on this confidence, that's the same problem. Based on, and by the way, this is a good problem. I like it. Both of them work. Based on the confidence interval constructed in part A, is it likely the mean reduction in cholesterol is less than 0.87? Oh, if you're going to claim that the drug is not that effective, please show me your study. Please show me your numbers, because mine says 0.8 is minimum of 0.89. You're saying that's not that good. It's only 0.87. Like, please show me. Okay. So we're going to say, no, that's not quite as good. So it is not likely to be less than 0.87 because our interval doesn't include 0.87. Okay. So there we go. All right. I think that's probably enough for one video on confidence intervals. That gets us started. There will be more actual content in the next video because there's some things we still have to do of population size. And again, the first problem, the first one of these is actually one of the, I wouldn't say it's a harder problem. It used to be, but it's still not, it doesn't fit in the same mold that the rest of the problems do. Okay. So tune in for the next video. There'll be more stuff to help you do your homework rather than just doing the homework problems. There'll be some more content. Like you need to do this. You need to be able to do this part to be able to solve this problem, kind of a thing. All right. So we'll stop there and we'll tune in for the next one, and I will see you then. Thank you.